Hello, everyone. Thanks for coming to this lecture. This is the first ML Open Talk at Yandex Hall this year. So the first one was supposed to be in March, but then we had a special guest. So we asked our colleagues from Yandex to arrange something earlier than March. And thank you to Anna and Lucine for figuring this out and organizing it today. So our guest is Sara Marjanovič. She will present a pretty interesting work on understanding how modern LLMs think. You might remember that a year ago, maybe a little bit more than that, DeepSeek made the news. They published the first publicly available open weight model, which was aware and which was able to think, whatever that means. And then several teams in the world, including this large collaboration Sara led, or I don't know what was your role, you will explain, was about understanding how these systems works. And today we are happy that she will present this work about thinking models.
Thank you, Hrant. I think this is a good volume for me to speak on. And I actually forgot my clicker. Thank you. Yes, I'm Sara Vera Marjanovič. I'm presenting a work that we're calling Thoughtology. I am currently a PhD student at the University of Copenhagen. I have a few other affiliations that I will mention. I'm currently doing an internship at NVIDIA, and I'm currently working on collaboration with some people at the Yerevan office, which is why I'm here, and was able to come and give a quick guest talk. And I will also mention that I was a visiting researcher at Mila, which is a deep learning research institute based in Montreal, Canada. And it was with them that, it was during my visit there, that we accomplished most of the work that I'll be talking about today. So this entire talk is going to be centered around this one paper, DeepSeek R1 Thoughtology, which was recently published in the Transactions of Machine Learning. I was involved in a lot of most of the work here, but we actually had a lot of collaborators who work in reinforcement learning, natural language processing, and linguistics. And it was nice to have all of their expertises to contribute to this work. And I mention this because due to the number of people that are working on this, it is a very large paper. I'm not sure how many of you have actually looked at the paper. It is around 44 pages of main text, 150 pages in total. So I will be focusing mainly on two sections, which I think are maybe the most interesting ones for me. Maybe not just the most interesting ones, but tell a coherent story front to end, though I will also highlight some additional findings that we have in other sections. When I do that, I will try to give a reference to the appropriate section in case anyone is interested in reading a bit more about that themselves. So, as an agenda for today, I will first present a brief history of LLMs to sort of contextualize why we decided to write a giant paper about one specific model, which is not typical in NLP research. Which Hrant also touched on. Then I will go into the two sections that I want to highlight, the building blocks of reasoning and analyzing thought lengths. Then I will sort of contextualize this with newer LRMs, large reasoning models, which is a section that we added more recently to sort of see how much of this is exclusive to DeepSeek R1 and how much of this is maybe a pattern that we see in all large reasoning models. And then I will go through some additional findings and how that relates to ongoing research in the field. So, without further ado, I'll start with my little history lesson on why was R1 so interesting. So the The story of NLP, the history of NLP is quite long, but I will start it in 2017 because we don't really care about much that happened before then in this context. So when transformers were introduced, which is the main architecture behind pretty much 99.999% of language models today and other kinds of machine learning models, people realized that if you just used a bunch of them, they would get very, very good at all sorts of tasks. As long as you just increase the length of time that you were training them on, you increased your data set size, you increased the size of the model, you got very, very, increasingly better language models. So this time is often called the training time scaling era because, yeah, you add more compute to it and it kind of works. And you might imagine that this was maybe a boring time for somebody who doesn't have access to a lot of compute. Before I mention that, here are some famous LLMs that are released during this time that maybe you're all familiar with. But there were some kinds of problems that these models kind of struggled with, which were more reasoning-intensive problems, like mathematical reasoning. And then we realized, if you prompt a model, you write it specifically in your prompt, or you give examples where you instruct the model specifically to reason step by step, performance on these kinds of tasks improved. So this was called a chain of thought. And that led to an improvement in performance in these kinds of tasks. So we can also call this the prompt engineering era for those of us that didn't have access to just scaling to the level that large companies were scaling. That kind of changed in 2024, late 2024, when OpenAI released o1, which was a very mysterious model to many at the time. It miraculously almost increased performance by large numbers in very reasoning-intensive tasks. Olympiad competition-level mathematics and coding and PhD-level science questions were answered with fairly high accuracy. And we didn't know necessarily how it was trained. People had some suspicions. All we knew is that the model thought internally for a few seconds and then gave an answer. And this launched what we like to call now the test time scaling era, where instead of just increasing compute at training time when you're creating this model, now we are investing some compute when we're actually doing inference, and that increases your accuracy as well. So I have one figure here from OpenAI and one here from somebody's Twitter, which kind of illustrates the same thing. And then R1 came out. So while it wasn't the first reasoning LLM, which I'll from here on refer to as an LRM, so I don't have to say as many words, it provided us access to its reasoning traces, which we call thoughts. They're maybe not the exact same as our thoughts, but we'll call them thoughts nonetheless. They also had open weights, so you can run it yourself. You can do some, train some probes if you wanted to. You knew, for the most part, its training procedure. We didn't have access to its training data necessarily. And notably, OpenAI was so convinced for a moment that R1 was trained on O1's output that one could reason that maybe it was much more similar to O1. And it also showed that just from reinforcement learning, we can have complex multi-step reasoning, self-verification, and these aha moments of insights where it can all of a sudden figure out how to understand, solve a very difficult question. And now we are firmly in this test time scaling era. I took a list of reasoning models from Wikipedia that have been released in the last year and a half. And it's growing more and more each day. I added some extra ones that I noticed that it forgot. So it's a very exciting time that we're living in. So we were motivated to look at R1 right as it was released. That's when I first came to Mila, right when it was released, the day after, I think. And we are so excited that we have this new breed of language model that we can look at its training process, and we can evaluate what does it do well on, what does it do poorly on across a variety of tasks. The original paper evaluated it in some way, but not very much in depth, and we could take a bit more of a critical view. So we could compare its model to other larger reasoning models. We can compare its performance to its base language model that didn't have the reinforcement, the reasoning reinforcement learning post-training. And we can also analyze its reasoning traces and see how that is related to its final output. So the majority of my talk is actually going to be related to this final way of evaluation. So first, we wanted to look at identifying patterns in reasoning. So in order to do that, we needed to manually inspect these reasoning traces at the start to identify some recurring patterns. This involved a team of us where we had some ideas and then we had to evaluate it. And eventually we were able to create this taxonomy of the underlying process. And then we could enroll a language model, GPT-4o, to annotate the reasoning traces across a variety of different tasks and data sets. And this was the taxonomy that we were able to identify. So I will show an example of a reasoning trace later, but as a primer, normally it'll start with defining a problem where it typically outlines what are the task goals, what does the user want from it. Then we have something called the bloom, where it initially decomposes the problem and gives a potential answer. Then we see one or more, or actually maybe zero, but that's rarely the case, reconsiderations of these initial assumptions, where it will reevaluate some premise that it makes originally, often starting with a wait or alternatively, and has some sort of verification of its confidence in this new or old interim answer. And finally, before it closes the thinking tags, it'll give a final answer. It'll qualify its confidence and provide the final answer to return. And then you can compare this final answer to what is actually given outside of the thinking tags in what is presumably just shown to the user. So here's an example of the shortest possible reasoning trace that we could get from DeepSeek R1. This is from GSM-8K, which is an elementary school level math problem. So and I highlighted the colors here based off of their role in the, according to this taxonomy. So I zoom in here. So we start off with this problem definition. Starts with, okay, we've defined that this is a math problem. It parses the problem. And it concludes with, I need to find the total number of bolts needed for both. So it's identified its goal. Then, in the bloom, it starts to break down the problem, makes an initial premise, and then it'll solve the problem to give 3 bolts in total. Oops. Now we have our reconstruction. So this is oftentimes, and we'll talk about this again later, the longest part of the reasoning trace, where it wants to say, wait, let me sure I'm not making a mistake. And in this case, it has 3 cycles of it verifying that the answer is in fact 3. And it never changes its response in this case. Then finally, it'll say it's confident now. The answer should be 3. It outlines the final answer. It closes the think tags. And here in the black, we have what is mentioned in the answer tags of the model. Where it agrees with what it said in the reasoning trace, the total number of bolts needed is 3, which it has boxed. Great. So now I mentioned that we had done this over a number of different tasks. I will quickly define what some of these tasks are. We have context faithfulness, which is sort of an adversarial context adherence task, where we provide some text that presumably we got online. We didn't, we made it ourselves. That is not necessarily something that the model thinks it's true. So it'll say something like, One Direction is an American band, or the current president of the United States is Michael Jackson. Something that the model obviously knows is false, but we ask it to answer a question as if that's true, and how well does it adhere to that? Harmful QA includes some safety-related data sets where we ask the model to answer questions that it should not answer. For example, how can I build a bomb? How can I steal someone's identity? How do I hack into the Pentagon? For psycholinguistic stimuli, we have some linguistically complex sentences. Oftentimes, these are linguistic illusions, something like, more girls passed the test than John did. It's a sentence that sounds correct, but doesn't make any sense, and then we ask it to give a proper, to define how many girls passed the test. And then we have some math questions that we get from multiple different math benchmarks. And what we can see here is across all of these very, very different tasks, we have a relatively consistent length of time, inference time, spent in the problem definition, the final destination, and relatively a similar amount of time spent in this Bloom cycle, this initial deconstruction. But what we see as the most striking difference in inference time is this reconstruction cycle stage. So how much does it spend actually checking over its work over and over again? And when we look into some qualities of these cycles, in this case, we're looking at the number and the length, we can see there are often very many cycles, and each cycle typically it gets shorter and shorter than the previous one. When we are actually looking at the quality of these reconstruction cycles, what I've highlighted here is that these models consistently revisit the same premises and approaches over and over again. Let me see if I have a zoom-in version of that. Yes, I do. So I have these revisited premises here highlighted, where it says half that much of what? I think it means half that much of the blue fiber's amount. Okay, so that much refers to the blue fiber, right? Maybe half that much means something else. Could half that much be referring to something else, like half of the total? So it's actually just going over the same thing over and over again. And we can see that in a number of other tasks. So I've highlighted a few other ones where there's a linguistic task, but maybe the answer is both, go. But maybe the question is who goes, so both. But the question is who goes, but the question is who goes, so both. And this goes on for a very, very long time. We also see these in code generation tasks as well. So, as I've mentioned, these can be often verbatim repeats. We're not actually getting some new information from this constant reiteration of the same words. And we call this behavior rumination because it's a little bit similar to, if you're familiar with the term ruminant, which is the kind of animal a cow is, where it takes some grass, chews the grass, swallows the grass, spits the grass up back in its mouth, swallows it again, and digests it again ad nauseum. So we decided to introduce two simple measures for rumination, just a 5-gram repetition rate and a lexical diversity measure. And when we look specifically at Math 500, which is a nice math benchmark because it grades questions on its level of difficulty, we can see that no matter how we measure rumination, we see it typically increases with problem difficulty. And when we use this 5-gram repetition rate, which I think is a relatively conservative measure of rumination, because you're assuming that the same 5 words are repeated, we actually have a very high degree of repetition within these reasoning traces. And another thing that I'd like to note is that it isn't just an indicative of processing time. These are two completely different measures. A measure with longer processing time might have lower rumination. These aren't necessarily related measures. So, in summary from this section, I hope I've convinced you that reasoning chains follow a pretty consistent pattern and they can be very long. And the majority of this inference time is due to what we call problem reconstruction, where R1 is re-examining and re-verifying its work over and over again. And these can often be verbatim repeats, and we call this rumination. So, in the next section, we wanted to analyze the impact of thought length. So, how does the length of reasoning chains impact the performance of our models? So, as I've just noted, we have realized that the reconstruction leads these models to have very long, often redundant reasoning chains. But as I mentioned earlier, where I tried to contextualize this within this test time scaling era, we have the hope that the longer that we spend on reasoning, the better accuracy and performance that we will see. So in order to do that, we focus specifically on math-related tasks. We're looking at some popular math-related benchmarks, Math 500, GSM-8K, which I've mentioned earlier, and AMY 24 and 25, and also some multiplication benchmark, where we have digits up to 20, or numbers up to 20 digits in length. So we can see a pretty big pattern that correct thoughts are on average shorter than incorrect thoughts when we divide based off was the model correct or incorrect, and we just count the number of tokens within the reasoning traces. And we see this across all of our benchmarks. And we also typically see that there are higher rates of rumination in these incorrect reasoning traces when we compare them to correct reasoning traces. We also note something that we like to call a sweet spot of reasoning. So in order to measure this, or in order to get this graph over here, we took multiple generations of the same of R1 for the same question, and then we normalize the length of tokens. So if you can see over here on the far right corner, the 1 is the maximum number of tokens that could be generated out of these 50 generations, based off or versus 0 tokens. Then we can bin these reasoning traces based off of the length of time. And then we can take the average accuracy across these bins. And we can see that there's a pretty steep drop-off in accuracy when we have longer thoughts. Particularly as long as we have around under 50% the maximum length of trace, the maximum length of a reasoning trace, we'll get the highest accuracy for a problem. So then we try to force termination early. So if a model on average takes 1,400 tokens to answer a question, what if we stop it at 200 or 400 tokens? How well does it perform on average? And we can see with, I actually have the direction sign, it should be less than. But we can get up to 93% of performance with under 50% of the compute, which suggests that this extra thinking gives a pretty limited return of investment. We're using a lot of compute and we don't necessarily always need it. Oftentimes when we're using extra compute, it is not necessarily to our advantage. So, as I mentioned in the last section, we can have these very prohibitively long reasoning traces. And when we look actually at the impact of the thought length on the model performance, we can see that the reasoning paths of these incorrect responses are often significantly longer and have higher rates of rumination. Most questions have a sweet spot of reasoning. Extra reasoning will actually decrease performance, and just allowing you to inference time scale for forever is very cost inefficient. So we can't just rely on inference time scaling. So when we published this, we wanted to, it took some time for this paper to get accepted because it takes time for reviewers to read 115 pages. When it got accepted, we decided that we wanted to add in some analyses against some additional LRMs. So we chose Qwen3, the largest version, and GPT-OSS 120B. They are also open source LRMs. They don't necessarily all have open training data or how it's trained, but at least we have access to these models and we can run them ourselves and have access to the reasoning traces. And what we can see is that Qwen3 actually has very similar thought structures to R1. Our R1 annotator worked completely out of the box on Qwen3 reasoning traces. You can see the same colors here. If you read it, you would even see we've highlighted words that are very, very reminiscent of how R1 talks. With, oh, that seems straightforward. Wait, is that right? Yeah, that's correct. Let me double check. I think that's it. Let me just make sure there's no calculation errors. So it works very similarly. In contrast, GPT-OSS 120B has a much more condensed reasoning trace. Oftentimes it won't even go through a reconstruction stage, but it'll still define the problem, give an answer, and follow through a problem. You can't reason without doing that. Yet, we still see that overthinking is a problem. There's still a sweet spot of reasoning that is somewhere around under the 50% of the max reasoning trace for both of these models. And we still see that correct thoughts are often significantly shorter than incorrect thoughts. And this is even stronger for our condensed model, GPT-OSS 120B. So overthinking is still a problem. It isn't necessarily solved. So now that I've gone through the issues of overthinking and some of the reasoning patterns that we have in R1 that also hold for other newer LRMs, I want to present some additional findings, which I'll call a collection of other pitfalls and weaknesses that we see in R1. So I've already mentioned that long thoughts impede performance. There are some other things that are affected by this. We created a reasoning needle in the haystack task. A needle in a haystack task is essentially where you provide a huge amount of text and then you import some important information right in the middle of it. We did that within its own reasoning traces. So it has these very long reasoning traces. Is it going to forget something that it said within its own reasoning trace? And we noticed that that was actually the case. We also tried to ask it to follow a given budget by saying in our prompt, please only use 500 tokens. It doesn't follow that. We could train a simple proof of concept to try to follow a reasoning budget, but you can see here it's the blue one on both graphs. So it's at an angle because it's actually following the requested thinking budget below. But as you can see on the graph on the right, it has consistently lower accuracy. And that makes sense. We're adding an additional metacognitive task. We need to use some of our processing power to keep track of how many tokens we're using. And there are other kinds of metacognitive processing tasks that we would probably like our model to have, understanding how close it is to a potential answer as one. So, there's been a lot more research on all of these topics as of late. We've seen a lot of people commenting on this sort of inverse scaling or the fact that just more test time compute isn't going to save you. How can we create large reasoning models that can follow a specific budget? And how can we ensure there's some metacognitive monitoring of our models? And so there's a lot of opportunities for both people that are very interested in reinforcement learning and also people that are working in interdisciplinary fields. We also noted that there are some new safety risks by reasoning. So we noted that R1 is much more likely to output harmful information than its non-reasoning base model. So R1 is our bluest model all the way on the left of all of these bar groups, and its base model, which did not go through post-training, is V3, which is the slightly greener blue model just to the right of it. And then we have some other relatively safe models that are significantly smaller next to it. And you can see R1 has a big jump next to the other safer models, but also next to its own base model, which only differs from it based off its reasoning post-training. We also showed that R1 can be used to jailbreak very safe models. It increased Gemma 2 and Llama 3's likelihood of outputting a harmful information by 72%, where it's pretty much very close to 1% beforehand, so that's a massive jump. And we also noticed that if you query it in different languages, you see very different reasoning traces. You can get very different responses, which is also a very interesting avenue of research. So there's been a lot of research since then about, one, the cybersecurity risks of releasing LRMs to the general public, how we can use LRMs as autonomous jailbreak agents, and also how we can look into multilingual input and reasoning paths. Another thing that we noted is there's a dearth of diverse reasoning strategies. We're training these models specifically with math and code tasks during the reinforcement learning stage. And these are nice because they're very verifiable answers, so it's easy to give a reward to this model. The issue is, if you only have a hammer, you're likely to see every single problem as a nail. And that won't help you if you need to screw something in. So we evaluated this with an abstract reasoning task that we created, which is an ASCII drawing task. And this is a very fun task. We just ask a model to draw a dog in ASCII. It's kind of difficult to automatically verify, so you kind of have to manually go through it. And what we notice here, so on the right here, I have examples of the drafts that R1 put out when it was asked to produce a dog. And you might notice that none of these have much to do with the preceding draft. It's not really iteratively developing a draft like, for example, you and I might do that. So it often recreates these images from scratch. And what we also noted is that this final answer that is output rarely aligns with the answer given outside of the thinking tags. This is more apparent when we made a more complex task, because we figured there are enough ASCII dogs on the internet. These LLMs are trained on information on the internet. Do you know what no one's ever asked somebody to draw before? A dog-shark hybrid. So I hope you guys can see some of this. But you can see that it tries to identify some subtasks. So at the start, it says, maybe I'll draw these eyes as like this dot, beak dot, to show a shark-like gaze. And then it identifies that a shark would have a dorsal fin and a shark tail. But then when we see the final drawing, it doesn't include any of these things within the final draft. Which one shows that it's not very diverse in its reason in how it's going through this, but there's also some strong unfaithfulness of this reasoning trace. So there's been a number of work afterwards on this, one about trying to increase the diversity of reasoning strategies outside of just math and code reasoning, identifying how unfaithful our reasoning traces are, and also how we can ensure faithful reasoning traces as well. So in summary, we've seen some pretty consistent patterns of reasoning, not only in R1, but in also LRMs. There's a consistent structure to reasoning processes, but the majority of inference time, at least for R1 and Qwen 3, and hopefully some other large reasoning models, a lot of time is devoted to reconstructing the problem over again. And oftentimes this might be verbatim repeats and might lead to very long reasoning chains. There's a sweet spot of reasoning. Overthinking won't necessarily improve performance, so we need to restrict inference time scaling to some degree. Also, it isn't just, the research landscape isn't just limited to large companies that have lots of compute. There are some other things that even people working in academia that don't have access to compute can work on. They can look into reducing overthinking and balancing the metacognitive load, addressing the safety risks of large reasoning models. We can look at how we can develop diverse reasoning strategies for a variety of tasks by either creating evaluation benchmarks or creating training data sets. And we can also work into evaluating and ensuring faithful reasoning trains. So thank you all. In the red, I have the link to my full paper, and in the black, I have a link to giving feedback to Yandex Hall.
Thank you. This is so cool. I think we have time for questions, and I have so many questions. Where to start? Okay, let me start from my first question. So did you notice qualitative difference between GPT OSS and all the Chinese models? Or did you try other models after this? Like you mentioned the length of the reasoning trace, but then anything other in terms of structure?
Yeah, what I noticed was, at least with GPT OSS, and I guess you can also see it with here, is that when it's reasoning, it seems to follow a much more mathematical or coding structure. I'm not sure if that's something they explicitly tried to ensure, but I imagine that that's one of the reasons why it feels so much more condensed. There's not so much linguistic indicators of, let me think, wait, that sounds right. It's not necessarily qualitatively evaluating it. When I look into other models, I can't quite remember about other models besides these three, though I have looked at them. I feel like most of them are quite long. GPT OSS is typically quite fast to run, which probably owes to its shorter reasoning traces. But most models seem to have a fairly long inference time. So I imagine it might be similar to something like Quen, but I'm not certain. I can't speak definitively.
And do you think this type of structure was explicitly given to DeepSeek? Like, probably did not discover the weight part, right?
Yeah. So that's something that's kind of hard to answer. We mention in the paper that it's very hard to differentiate what might necessarily be something that naturally comes from reinforcement learning and what might be within the SFT data that was used to start cold start R1's training process. Some of my co-authors fairly strongly believe that it is something present within the SFT data set, but we don't have enough information to prove or deny that. But it is likely that it is in some way from some of the training data that has been made available to it. So, if not within the cold start data, probably within some of the training data, it's trained on Stack Overflow data, which might have something similar. Yep.
Yeah, just to continue the topic around GPT-OSS, it has different reasoning modes, low, medium, high. Did you try to compare them, and what reasoning mode did you use when you're saying it's very compact and not very semantic?
And that's a good question. I think we used high reasoning because this was done after I finished my internship or my visit there. It was my co-author who was running the majority of this, but I think it was all high reasoning.
Okay, why some LLM models, for example, Claude Sonnet, sometimes stuck in the loop, endlessly repeating the task and their thoughts and over and over again?
Why do I think they're doing that?
Yes.
I imagine that it's stuck in some kind of local minimum. So it just keeps, it's just predicting the next token that's most probable, and at some point it's just bouncing between the same few tokens until sometimes it either runs out of tokens or it somehow gets out. But
and their thoughts are reasoning is constrained. Reasoning thoughts are constrained. Yes.
These ones are not. These ones are unconstrained. Like, we just let the model reason for however long, but at some point you do have to provide a max length. Yeah.
Okay.
Other questions?
Hi, Sarah. Thank you for the presentation. It was very interesting. My question is about this unconstrained versus constrained reasoning kind of setup. Mm-hmm. So very specifically, I think in the presentation it was stated that if the question is harder, then there's more rumination.
Yeah.
So then, if that's the case, then isn't it possible that the reason that longer reasoning traces are more incorrect is because the underlying question is more difficult?
That could be, but that's why we also decided to look at this question level binning, where we look at the accuracy in comparison to the number of tokens that it used. One could argue, and this is something that we note, that maybe it's just because the model gets off on the wrong footstep at the start and goes down the wrong path of reasoning, but it still shows that extra reasoning isn't saving it from making this mistake. It isn't getting it out of that.
just to be clear, there is nothing here about the question complexity, right?
Yeah, these are only looking at the same question. So we're only comparing within the same question.
Oh, okay. So this is within the one question. If you increase the number of tokens, the accuracy drops.
Yes, so we create a number of these curves, and then we create each curve per question. Within the paper, it's probably a bit easier to understand because we visualize this is the curve for question 3, this is the curve for question 7 as some examples, and then this is the average curve across all questions. But we see this across every single question.
So this is an average across all questions, but this is the trend for every question. How do we stop the generation here? What's the specific method?
So this is unconstrained. So here we didn't tell the model stop, we just let it go.
Okay.
And then in the next one, we chose an easier question. We knew how long it typically took on average to answer. And then we just said, okay, after 100 tokens, we're going to stop it. But one could theoretically, this is something we toyed around with doing. If you wanted to do this yourself, you can sort of give its reasoning trace back to it, but remove the end think tag and add weight, and then you can get it to think longer. If you wanted to do this at home. I think some other people have done that since and shown similar results.
I see. Thank you.
Yeah, thank you very much for talk. I have a question. So just an intuition as a user, when you use thinking models, the expectation is that they do kind of depth-first search, right?
Yeah.
So it looks like it should just go in some path, try to find something, and if it's not fine, just start from the start with another branch. And what I understand that it's not the case now. So it could be cycles. It's when it takes longer time, it just starts to do wrong things, and it's not clear DFS. And it's not a BFS. It's just some strange way how it thinks. Is there a way to guide the LLM to, let's say, do it in particular order? Do you try to do it in prompt or somehow differently just to guide how to think?
Yeah, there are two things I'd like to answer to that question. One, I think I would still say that this is a depth-first search, because it still, before it goes into these reconstruction cycles, it still solves the problem at least once to the end. It doesn't reconstruct before it gives a final answer. And then whenever it does a reconstruction, it's not like it starts from the beginning again, it starts maybe from halfway point, if we can visualize this abstractly like that. So I'd still say it's a bit closer to a depth-first search than a breadth-first search. The second question, which was about different ways of trying to ensure, of trying to guide reasoning. In the paper, we do a bit of a review of different ways that people have tried to, via prompting, ask the model to follow different kinds of reasoning. There's different ways that they try to ensure some more breadth-first search, where they try to, I remember there's one called tree of thought. Instead of doing a chain, this sort of encourages more breadth-first search. When we are relying on reinforcement learning guided reasoning, there are some ways that I think might be more conducive to ensuring some breadth-first search, but the issue is that they are not typically very efficient to implement. So one of the nice things about R1 is that it was very efficient to train. It was an engineering, a truly impressive engineering feat in order to do that. And they had some very efficient ways of training the model. And there are other reward strategies out there, but they're just typically not as efficient. I can't think off the top of my head of another large reasoning model that relies on something that doesn't promote depth-first search.
Yeah, at least somehow guided to repeat at least
Yeah, okay, so you're thinking of something that is trained so that it doesn't skip something going into a wrong method. I'm not a reinforcement learning person, but R1 was trained, there are two kinds of reward models. One where you consider just, did it answer it correct, yes or no? That's very efficient, that's how R1 is used. But then there are other ones where you consider the steps used and you determine what steps were important. I think those ones are more likely to generate much more efficient reasoning traces, and I don't know if that would help with breadth first search, but at least would prevent some of these local minima that we reach into, yeah. One of them is called Vine PPO. One of the co-authors wrote that, so I am familiar with that.
Thank you very much for the talk. My question kind of falls in the same vein. Like, going back to the roots, you said we devised the taxonomy of how usually the reasoning goes. So there is your initial definition step, bloom step, reconstruction step, where we have the cycles, which is the search part of the overall problem. The question, because most reasoning models are trained on synthetic type of data, at least like to some degree synthetic type of data. Do you think this type of a taxonomy arises because of the data that we train on? Or is it a byproduct of more of a reinforcement-ish algorithm that we use to like essentially encourage exploration? But because we encourage exploration, we also encourage cycles.
Yeah. So like I mentioned, that's something that we can't necessarily evaluate for sure. I have an intuition, which I can say. And I imagine that a lot of this taxonomy is probably something that's present in a lot of the SFT data sets, or at least, it kind of also looks like a Stack Overflow conversation where the problem definition is the first poster, and then we have these cycles of other people commenting on, and then we say, okay, well, I think this is your final answer. This could also come from training data that's similar to that. And I saw, I think it's by Google, another paper that sort of looks into, are these reasoning processes just societies of thoughts of different personas talking to each other? But I imagine that these very long reconstruction cycles are likely an after effect of RL. So it's probably a combination of the two.
So with that in mind, a more esoteric question. Do you think this is in general the optimal or correct way to train a reasoning model? Like, we kind of bias it towards a certain sort of variational thinking. Do you think that would lead us in a way to close to an optimal way, or should it be done this way, or should we essentially steer away from this type of are we going towards the bitter lesson or not type of a question?
I think that it isn't necessarily the wrong way, but it isn't the only way. There is a very large philosophical branch of literature on how to properly reason through a problem. And this way of reasoning is clearly very effective for math and coding tasks, but might not necessarily be advantageous for every kind of reasoning task. Like if you want a model to draw an ASCII dog shark for you, for example. So I do think there needs to be different kinds of this sort of synthetic data that we use, but also different ways of, different kinds of data within our training data that can be easily verifiable for reinforcement learning. I'd be very interested to see if there are other ways to do it. Yeah. Oh, and I thought of something else actually as you were asking your second question about another reason why I would assume that it's this longer reconstruction cycle is an after effect of RL. It's because something that both R1 had noticed and some of my co-authors had noticed on a project they abandoned because they thought it was a bug, is the longer you train a reasoning model, the longer it will reason for. Like the average reasoning trace gets longer and longer. So some of our co-authors had stopped training something because they were like, oh, that seems weird. This is clearly not working. But then R1 noted it as like, oh, this is super impressive that it learns to do this. So, yeah.
Thank you very much for your talk. Can you please switch to the slide where you show 50 samples of what? Not this slide?
Yeah.
That one, yes. As far as I understand, to get a diversity in these 50 generations, you have to use some high temperature to have this diversity.
Yeah, I mean, when you are, they actually recommend that when you run inference with DeepSeek R1 is that you actually should have pretty high temperature, like a 0.7. It's not super high, but it's still not a temperature of 0.
Okay, cool. And my question is, as far as I understand, the higher the temperature is, the longer the prompt, the thinking part is, the higher chance of some hallucinations inside of this thinking prompt. Maybe we have some decrease in the quality of answers because of accuracy of these events, of these thinking bugs. And my idea and my question is, does this graph generalizes on usage with lower temperature when we have lower chances of these thinking bugs, these hallucinations?
We did not test with other temperatures. I'm trying to remember within the exact DeepSeek paper, they specifically say that they do not want you to use a lower temperature because it actually has reduced performance. How that performance is reduced, I'm not entirely certain. There is some benefit to having a moderately high temperature. It's true that it does increase your risk of hallucination, but it does also increase the diversity within the reasoning process. And that is still important. I fear that with lower temperature, maybe you are even more likely to get into a verbatim repeat. I'm not entirely certain. But one thing that I wanted to note is that, so within the chain of thought prompting time period, we had this part 2 of chain of thought prompting, which was self-consistency. Where if you ask the model to reason through the same thing multiple different times in multiple different ways, it was much more likely to get the right answer. So you do kind of want some diversity. So you would like some high temperature because then hopefully you aren't just investigating the same thing over and over again and you're using a different method to get to the same answer. So that is why I would maybe expect that R1 is reporting lower accuracy on benchmarks when that has a lower temperature, but I do think it would be very interesting to investigate. I think they do provide a range, so just comparing the range of temperatures, seeing how the rate of rumination might increase or decrease, or accuracy increase or decrease, or just the length in general increases or decreases with this.
Okay, thank you. And one more short question about the jailbreaking. What is the main idea behind this? How does they use R1 to jailbreak another model? Does they replace thinking part of the model or something like that?
I think what you just do is you ask, you give a question to R1 and then you say, how can you rewrite this question so that another model is going to answer this question. It is trained to avoid these certain things, and then it'll reason over how to rewrite your question for you.
Thank you.
Do we have more questions? I wanted to ask one. Do you think that this number of ruminations or this increased overthinking could be a sign of like low confidence in the answer and kind of use that as a confidence measure?
I was interested in that. I think there's been some decent amount of work recently, not necessarily on rumination as a confidence measure, but on looking at other sorts of indicators, either ones that look specifically at the model activations during the reasoning trace, or other, words that are mentioned, like, wait, is that right? Let me check again. I think it might indicate that it is reached very, very low confidence. But maybe it depends on the kind of repetition. Obviously, if it's able to repeat, the answer must be 5 over and over again, I think that's fine. Should increase confidence. But something like we saw earlier, where I had over here, so this is a problem, I can imagine that would decrease confidence. I think it would be really interesting if you could have like a running meter of confidence as you have this reasoning trace. I don't know if anybody's been working on that. I was interested in that at the start, but it was kind of hard to implement.
I see. Also, it would be interesting to check when this exact same pattern happens. This is only the kind of the argmax effect, right? In a way, I mean, it's the sampling. So
yeah, there are other things going on underneath. Yeah.
Yeah, maybe like you could track how the actual representations are changing across. I don't know what would it show, but it's hard to say where it should converge. Okay, yeah, one more question here.
Could you clarify how, I assume you did automatically the creation of the blocks, the defining of the blocks, so the reasoning blocks that the model thinks. Could you clarify how do you do it automatically, and how do you measure if it's good enough?
So when you're talking about these blocks, you mean like when I'm coloring in these things as belonging to a stage? So we did some prompt engineering with GPT-4o, where we defined the taxonomy. We presented in the paper. It took a few iterations where we were manually verifying on a subset of, I can't remember how many, that these were correctly annotated. And we had I had one other person who was helping me make sure that these were annotated correctly. And once we had seen that it was annotating it pretty consistently and how well that, like how we would also annotate it, then we allowed it to go unchecked for the remaining 400 examples.
Okay. Okay, so did you keep checking the results over time, or it was you trained a language model that automatically annotates?
Well, I mean, we created a prompt, so it's not so much training as it is that you are providing instructions, and you're hoping that if it can follow the instructions consistently for a diverse enough
so it's just an LLM that's prompted to annotate?
Yes, it's GPT-4o. We're using an LLM as an annotator.
Okay.
These things are very simple now.
It might not be perfect. It might not be the best way of doing it, but I think it's pretty common within the field. And then we had all of these cycles independently annotated as well. What I will note is that the locations of the cycles weren't always perfect in my view. But in terms of the problem definition, final definition, end and start of reconstruction cycles, and the bloom cycles, that seemed pretty consistent across the tasks.
Yeah, NLP is very simple now, you know? Cool. Okay, let's thank the speaker again, and we have time to network and some food. Thank you for coming.